Welcome back on Earth Geometry. Today, 3.3 CPCTC. That's not as confusing as it looks at a glance. And we're also learning about circles. So here we have a circle uh, inside what appears to be a square, but we don't know for sure if it is a square. We don't even know if that's a rectangle or not, right? It looks like it might be, but remember, we can't assume right angle, so we cannot assume that is a square or a rectangle. So first off, let's talk about circles. Here's how we name circles. We call them by their midpoint. All right, so, or the center, I should say, not the midpoint, the center. So the name of the circle would be circle D, right? So if I tell you that D is the center of this circle, you would call it circle D. Or if I tell you this is circle D, then you know that D is the center of the circle. So we're going to use the center to name our circles. Use the center to name your circle. So in this particular circle, we have radii. All right, so think about what radii are. All right, one of them is called a radius. So see if you can name one radius. One radius. How about that green one? What is that green one called? That is dB. All right, that is radius dB. Where's another one? Well, dA is another. And a third is DC. So these are the three radii that are shown in this particular circle. Quick question, how many radii exist inside of this circle, right? Seen or unseen? How many radii exist? The answer is there's an infinite number, right? So I can draw in a number of them. There you go. Oh, that's a bad one. But the point is, I could draw in an infinite number of radii inside of this circle. So there's three that are shown here, but there's an infinite number that exists in this figure. All right, now, by the way, the radius I didn't mention is the segment that connects the center of the circle to the circle itself. So from the center to the circle, that is the radius. Um, the diameter is the segment that passes through the center that connects, or that has endpoints on the circle. So the segment that passes through the center, so we're passing through segment D, and has endpoints on the circle. So AC would be a diameter in this figure. There's only one that is shown, but much like the radius, there are an infinite number of diameters that exist here. We can find the area of a circle using this formula. Area equals pi multiplied by the radius squared. So if we have the radius, that is enough information to find the area of a circle. That's all we need. We can find the perimeter of a circle, which is another word to say the circumference, right? So we'll say circumference or the perimeter. 2 multiplied by pi multiplied by the radius. Or think about what the radius is. The radius is half of the diameter, right? So if we take the radius and we multiply it by 2, you could say pi multiplied by the diameter, or diameter times pi. The area, like all areas, are measured in units squared, right? And the perimeter, or the circumference, is measured in units. So for example, if our radius were like 5 inches, 5 squared is 25, 25 pi, and then the units were inches squared, 25 pi inches squared. If the radius were 5, 2 multiplied by 5 is 10, 10 pi inches. So it would be inches squared for the area and inches for the circumference. Here we have a theorem. All radii of the same circle are congruent, or you might say all radii in the same circle are congruent, something like that. This is going to be used in proofs. This is a reason in proofs. All right, so this is something you need to commit to memory because you're going to have to draw upon this as we work proofs. So what would you write? Well, if for some reason you had to say dB is congruent to dA, dB is a radius, dA is a radius. If dB is congruent to dA, how do we know that? Because all radii of the same circle are congruent. Example 1, circle K. All right, here's circle K. Because we call it circle K, we know K is the what? K is the center. It has a radius of 14 centimeters. Find the circumference in terms of pi. Circumference is equal to 2 pi r. And if the radius is equal to 14, the circumference is equal to 2 pi times 14. So our circumference is equal to 28 pi. Were we given inches here? We were, right? So this is centimeters for the radius, and this has got to be centimeters for the circumference. So there is the circumference of that circle. Try to find the area in terms of pi on your own. If the radius is 14, what is the area in terms of pi? When it says in terms of pi, it just means there's going to be pi in the answer. Don't actually multiply by pi and then round it. So by leaving pi in our answer, we don't have to round it, which is nice. So go ahead and work B on your own. Well, area of a circle, area is pi r squared. All we need is the radius. We have the radius is 14 centimeters. So area is equal to pi multiplied by your radius of 14 squared. Might want to use a calculator on this one. 14 multiplied by 14 is 196 pi. So 196 pi. And the units are going to be centimeters squared. 196 pi centimeters squared. Okay. All right, this next part looks more confusing than it actually is. CPCTC, corresponding parts of congruent triangles are congruent. You'll commit this to memory pretty quickly. Corresponding parts of congruent triangles are congruent. CPCTC. So here's an example. If I tell you triangle ABC is congruent to triangle DEF, there's a number of conclusions we can draw from this congruency statement. One is, I'll just say then, segment AB must have the same length, or it's congruent to segment DE. AB is congruent to DE. How do we know that? Well, because corresponding parts of congruent triangles are congruent. This would be a reason in a proof. All right, proof, reason. CPCTC. All right. So what reasons do we have for our proof right now? We learned that all radii of the same circle are congruent. That's one proof reason that we might use today. And another one is CPCTC. So when we have two congruent triangles, and for some reason we have to show those corresponding parts are congruent, CPCTC is the reason that we would use in the proof. CPCTC. Example 2. Given circle C, A is the midpoint of TR, and we're trying to prove that triangle CAT, which is this triangle on the left here, is congruent to triangle CAR, which is that triangle on the right. See if you can do this one on your own. You might be able to. Challenge yourself, push yourself. We got a little bit of time here, so try this one on your own, and then come back to the video and see how you did. Pause the video now. All right, did you do this? If we know we have circle C, okay? Well, let me back up. What are we trying to prove? We're trying to prove triangle CAT, which is a triangle on the left, is congruent to CAR, triangle CAR, which is a triangle on the right. So we need to either use side, 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 side angle, side, or angle, side angle. Those are the three triangle congruency postulates that we know. So we need to find sides that are congruent, we need to find angles that are congruent, and we need to determine which, if any, of those congruency postulates we can use. So did you do this? Did you mark up the triangles and then go into the proof? I hope you did. Well, if we have circle C, we know that CT and CR have to be congruent because they're both radii. If A is the midpoint of TR, well, here's TR, and A is the midpoint, then TA has to be congruent to AR. That's the definition of midpoint. It divides the segment into two congruent pieces. And then what about CA? CA is congruent to itself. So we're going to be able to use side, side, side. One pair is CT and CR. The other pair is AT and AR. And the other pair is CA and CA. CA is congruent to itself because it's shared by both triangles. So number one, we're going to say circle C. That's given. Okay. And number two, we're going to say CT is congruent to CR. You were probably able to figure that out. What's the reason in the proof? All radii of the same circle. That's a bad thing, but you get the idea. Of the same circle are congruent. All radii of the same circle are congruent. Number three, back to the given information. A is the midpoint of TR. How did we know that? Because it was given. What does it mean for A to be the midpoint of TR? It means it's going to bisect segment TR. Well, that lets us know that TA is congruent to AR. How do we know that TA is congruent to AR? Well, because A is the midpoint of TR, and that is the definition of midpoint. It's going to bisect a segment. All right, what else do we know? Well, we know that CA is congruent to itself. CA is congruent to CA. Did you remember how we know a segment is congruent to itself? It's the reflexive property. Okay. And then finally, we're able to conclude that triangle CAT is congruent to triangle CAR. How did we know that? Because of the side, side, side. It's a bad SSS. Because of the side, side, side congruency postulate. Okay. How could you have done this differently? You could have lumped all the given information in together, and then you could have used all radii of the same circle are congruent to show that CT is congruent to CR, and you could have then used TA as congruent to AR. The order in which 2 and 4 happen doesn't matter as long as they come after what I had in 1 and 3. So if you lumped all the given information together, you could have had TA is congruent to AR first, and then CT is congruent to CR, whatever. Same thing for the reflexive property, right? This is assumed, right? So you could have thrown 5 in anywhere. So what I'm trying to say is there's a number of different possibilities for this, that like the order that you could have, but the meat of it, like what you said in the proof, like these are the only reasons that would be acceptable. All right. Oh, what happened? All right, I'm back. Okay, example 3. Given circle O. There's circle O. That means O is the center. It means OT is a radius. It means OC is a radius. Also, we know that OP bisects angle TOC. So here's angle TOC, and we know that OP bisects that. We're trying to prove that TP, here's TP, is congruent to CP. It's congruent to CP. So I would like you to pause the video, see if you can't think through this one. Remember to mark up the triangles first, kind of put together a game plan before you actually dive into the proof. And once you kind of have figured out what conclusions you can draw and why you can conclude those things, then start going on the proof and make sure it flows logically. So pause the video now and give this one a shot. Okay, here we have circle O, which means OT is a radius and OC is a radius. All radii of the same circle are congruent. I also noticed right away that OP is shared by both of these triangles. So that's another side that's congruent to another side. And OP bisects angle TOC. So that means angle TOP is congruent to angle COP. Okay. What are we trying to show? What are we trying to prove? We're trying to prove that TP, there's TP, is congruent to CP. So how can we do that? Well, if I can show these two triangles are congruent, the top triangle and the bottom triangle, if I can show these two triangles are congruent, then I can use corresponding parts of congruent triangles are congruent. I can use that to show that TP is congruent to CP. So I can see that these two triangles are congruent by side angle side. So let's use that as we work through this. Number one, circle O. Circle O. That was given to us. Well, because we have circle O, what are we able to conclude? We're able to conclude that TO is congruent to CO, or you might have said OC, whatever. The order in which those segments are written does not matter. And how do we know that? All radii of the same circle are congruent. Okay. What else were we able to conclude? Well, let's look at our given information. Let's go back to that. OP bisects angle TOC. How do we know that? That too was given. Number four, because OP bisects angle TOC, what does that tell us? Well, here is TOC. TOC has been bisected, meaning half is going to be here at angle TOP. Angle TOP. It's going to be half of it, which means it's going to be congruent to COP. COP. How did we know that? Definition of bisect. Okay. Remember the game plan. We're trying to show these two triangles are congruent. Then we're going to use CPCTC to show that TP is congruent to CP. A lot of C's and T's and P's in this. All right, let's keep going. Number five. OP right here is shared by both triangles. So we're going to say OP is congruent to OP. How do we know that? The reflexive property. Okay. Now we know these two triangles are congruent. I can see that I have two sides that are congruent, two pairs of sides that are congruent, TO and OC. OP is congruent to OP, and their included angles are congruent, angle TOP and angle COP. Therefore, these two triangles, triangle TOP is congruent to triangle, oh, that's a bad triangle. Like I do bad triangles usually, but that was especially bad. Triangle TOP is congruent to triangle COP. How did I know that? Side, angle, side. Congruency postulate. Okay. And then number 7, I'm able to conclude then that TP is congruent to CP. Notice the order that we have written our congruency statement. You got to be careful when you write your congruency statements here. So let's check our congruency statement. Let's take a look at T. What is T? T is where the one tick mark side meets the blank side. Now, we have a blank side and then we have the shared side, right? So we'll call the TP the blank side, we'll call OP the shared side, and we'll call TO the radius, or the one tick mark side, either way. So T is where the one tick mark meets the blank side. C is where the one tick mark meets the blank side. So T has to be in the same position as C. O, well, what is O? O is where we have the angle with one arc, right? So at vertex O, we have the angle with one arc, or you could say O is where the one tick mark side meets the shared side. One tick mark and shared side meet at O. What about in the bottom triangle? The one tick mark side and the shared side meet at O. So O has to correspond to O. Notice the two angles of vertex O are congruent as well. So that checks out. And then finally P has to be in the same spot as P. They are corresponding. Let's see why. P in the top triangle, that's the blank side meeting the shared side. How about in the bottom triangle? The blank side, CP, meeting the shared side, OP. So it checks out. We have a good congruency statement. You need to make sure your congruency statement is good. If you have a solid congruency statement, there's a ton of stuff you can figure out from it. If you have the wrong congruency statement, you're going to draw a bunch of conclusions that are not correct. Notice TP. TP is first and third. Notice CP. CP is first and third. So we're able to conclude that TP is congruent to CP because, see if you can remember, corresponding parts of congruent triangles are congruent. Yes, I will allow you just to write CPCTC. You don't have to write the whole long thing out. That is totally acceptable like that. All right? Very good. Example 3. In the words of the great DJ Khaled, another one. Example 4. Given E is the midpoint of RP. All right, well, here's RP. So we know that RE has to be congruent to EP. That's the definition of bisect. You know what? How about you try this one on your own? Pause the video now. I think you can do example 4 on your own. I believe in you. Do you believe in you? You should. You're pretty great. Try example 4 on your own now. Pause the video. Give it a shot. Unpause it if you need some help. There you go. Okay, we just talked about RE being congruent to EP. And the reason for that is E is the midpoint of RP. So it breaks that up into two congruent pieces. We also know that E is the midpoint of DN. Now, here's what I don't want to see. Do not put one tick mark here, one tick mark here. Here's why. What you're saying with this is all 4 of these pieces are congruent. That is not the case. We do know that DE has to be congruent to EN. We know that's happening, but we don't know if all 4 of them are congruent. They might be, but we are not able to conclude that from what we have here. Also notice angle RED and angle PEN, that'd be this angle right here and this angle right here. They are congruent because they are, do you remember? Vertical angles. Very good. So what are we able to, let's write a congruency statement here. We know these 2 triangles are congruent. How do we know they're congruent? Think about it. Well, side congruent to a side, side congruent to a side, angle congruent to an angle. Is this angle an included angle? You bet it is. It's where the 1 tick mark side meets the 2 tick mark side. It's the angle that is sandwiched between the 2 sides that we have information on. Same thing over here in the triangle on the right. The angle is sandwiched between the 2 sides that we have information on. That'd be the 1 tick mark side and the 2 tick mark side. So yes, that is an included angle. So we are able to use side angle side. Triangle on the left, let's call it triangle RED. Now be careful with the second part. Make sure that you put corresponding parts in corresponding positions. Let's take a look at R. Let's call these 3 sides the 1 tick mark side, the 2 tick mark side, and the blank side. Same thing over here. 1 tick mark side, 2 tick mark side, and the blank side. What is R? R is where the blank side meets the 1 tick mark side. That is R. Go to the other triangle. The 1 tick mark side meets the blank side at P. How about E? What is E? Well, E is where the 1 tick mark side meets the 2 tick mark side. Go to the triangle on the right. Where the 1 tick mark side meets the 2 tick mark side is also E. So E corresponds to E. And then finally, D is third. What is D? It's where the 2 tick mark side meets the blank side. The 2 tick mark side meets the blank side at N. So triangle RED is congruent to triangle PEN. It is important that you do that because we're going to have to line up. By the way, we knew this by side angle side, and we're going to use corresponding parts of congruent triangles are congruent to do this next part. We have information on angle R. What is angle R congruent to? R is first. P is first. We're going to say angle R is congruent to angle P. And I notice that I've got, well, in R and P, that's nice. They're both x's, so we'll just do this. 5x plus 10 is equal to 3x plus 18. We get 2x equals 8x equals 4. Very good. So x equals 4. What else do we have? We have angle D. All right, well, what is angle D congruent to? Angle D is congruent to, where is D? D is third. N is third. So D is third, N is third, so angle D is congruent to angle N. Angle D is congruent to angle N, that is 4y plus 13. That's angle D is equal to angle N, 7y minus 8. I add 8 to both sides, I get 21. Subtract 4y from both sides, we get 3y. And y has to equal 7, right? 3 times 7 is 21. There you go. We got y, we've got x. Very good.